In this lesson, we'll be talking about proofs by induction. What is the concept of induction? Induction is generally used to prove that some statement is true for all of the natural numbers with some lower bound on when we want it to be true. Sometimes we want this to be true all the way back at 0, and sometimes we have to start a little bit higher in order for the statement to be true. Officially, the theorem for proof by mathematical induction says that we assume a few statements are true. We've got P of A plus 1, P of A plus 2, all the way through P of B. And these are simply variables plugged into the statement that basically represent some of the early values in the problem. And then we assume this very important statement, that for all k greater than or equal to b, basically picking up where this one left off, P of k implies P of k plus 1. If we have all of these statements being true, then we know that for all n greater than or equal to a, all the natural numbers there, P of n, will be true. Here's how we use this theorem. First off, we need to prove some of these basic values. This is nothing different than just plugging in values into the expression and saying, is this true or false? Often we only need to prove the very first value and that's enough for these, but sometimes we need more than one. This is what we call our base case. Then we have our inductive case. The inductive case is proving this statement right here. So what I need to do is pick some k greater than or equal to b, assume P of k is true, and show P of k plus 1 is true. If I do that, then I have finished my mathematical induction, and I can now claim that the statement is true for all natural numbers, at least as big as a, where I started. Here's our first example. We're going to prove that as long as n is greater than or equal to 3, n squared minus 2 is greater than or equal to 2n. Again, we're going to use induction for this. So let's start off with our base case. The base case is letting n be the very first value, and possibly more, which we'll talk about later. Let n equal 3. Then let's plug it in. We get 3 squared minus 2. Well, let's see, that's equal to 9 minus 2 is 7. And notice 7 is greater than or equal to 2 times 3, which would be 6. That's all we need for our base case. Just plug it into the expression and make sure that it's true. Now for our inductive case. Again, you'll make the assumption that this statement holds for k and show it for k plus 1. Assume k squared minus 2 is greater than or equal to 2k for some k greater than or equal to 3. I simply plugged in k where n is, but one very important word I have in this proof is the word sum. I'm picking an arbitrary k here, some k greater than or equal to 3, and then I want to show for this arbitrary k that the statement holds for k plus 1. Let's write out what exactly I'm trying to prove. We want to show that instead of k with k plus 1 here, that k plus 1 squared minus 2 is greater than or equal to 2 times k plus 1. It might be meaningful to go ahead and write this as 2k plus 2. Now to show that, for inequalities at least, basically what you want to do is start on the left side and start simplifying. And I'll show you the steps as we go. Then k plus 1 squared minus 2 equals is what we want to do now. Let's simplify it. Well, k plus 1 squared, if you know your squaring theorem, it's k squared plus 2k plus 1, and we've still got a minus 2 outside. Now somehow I need to show that this is greater than or equal to 2k plus 2. And this is the idea. As soon as we can, we want to use what we call the inductive hypothesis. This statement right here, k squared minus 2 is greater than or equal to 2k, is a statement that I should use as soon as I can. It's my inductive hypothesis. Let me rewrite instead of simplify algebraically. I'll write this as k squared minus 2 plus 2k plus 1. Now pay careful attention to right here. K squared minus 2 I know is greater than or equal to 2k by my inductive hypothesis. what I'm going to do is say this is greater than or equal to, and my k squared minus 2 is going to be replaced with 2k. That's using my inductive hypothesis, so often I put a little IH above whatever symbol is being used, like the inequality or equal sign, just to say that I used the inductive hypothesis right there. Now I've still got the rest of the problem, is the plus 2k plus 1. Now let's look back at what I'm trying to show. I'm trying to show 2k plus 2 on the other side of the inequality. Well, I've basically got it. I've got a 2k, and as long as this is at least 2, I'm done. So why is 2k plus 1 at least 2? Well, you might look at the value of k. Remember that k was at least 3. So in particular, 2k plus 1 is at least 7. I really only need it to be at least 2, so let me just say this is greater than or equal to 2k plus 2, since k is greater than or equal to 3. Now I've shown my inductive case, and this finishes the proof. Often we just like to finish our induction with some sort of summary statement. Thus, by induction, n squared minus 2 is greater than or equal to 2n for all n greater than or equal to 3. And that is the end of our proof. Let's do the next example. 2 to the n is greater than or equal to n squared minus 1 for all n greater than or equal to 0. Let's start off with our base case. For the base case, we would start by letting n equal 0. But this time I'm going to think a little bit in advance, and I'm actually going to prove that this works for 0, 1, 2, and 3. Reasons for that will become clear later, but if you were doing this proof from scratch, you might try it at 0, and then if you run into a snag in the inductive case, you could go back and do some more base cases if needed. Note that 2 to the n is greater than or equal to n plus 1 for n equals 0, 1, 2, and 3 as follows. Let's plug them in. 2 to the 0 is equal to 1. Well, that's definitely greater than or equal to 0 squared minus 1, because that would be negative 1. How about 1? 2 to the 1. Well, that's equal to 2, which is definitely greater than or equal to 1 squared minus 1, because that would be 0. How about n equals 2? Well, then 2 squared is equal to 4, and 4 is definitely greater than or equal to 2 squared minus 1, because that would be 3. And then finally, let's look at 2 cubed. Well, 2 cubed is 8, and that is greater than or equal to 3 squared minus 1, which would actually be 8 itself. So at this point the two are equal, but nevertheless greater than or equal to still holds. This finishes my base case. And while it's not clear yet why I did 0, 1, 2, and 3, that will become clear soon. Now let's do our inductive case. Assume 2 to the k is greater than or equal to k squared minus 1 for some k greater than or equal to 3. Again, you want to assume this for some k and show it for k plus 1. Since I did all the way up to 3 on my base case, I can assume that k is starting at 3. This is the reason I went to 3. But again, it's still not exactly clear why I need k to be this big. You'll see soon. Let's write down what we're trying to show. I want to show that 2 to the k plus 1. Again, I'm plugging in k plus 1 this time. I want to show that's greater than or equal to k plus 1 squared minus 1, and I went ahead and simplified that to k squared plus 2k. Then 2 to the k plus 1 equals, again, just start on the left side, and try to algebraically manipulate it until you get to the right side. But as soon as we can, we want to use the inductive hypothesis. So somehow I need to manipulate 2 to the k plus 1 here. But I know that 2 to the k has some information about it, so somehow I need to get a 2 to the k in the problem instead of a 2 to the k plus 1. Let's use the reverse of one of our exponent laws. I can change this to 2 to the k times 2 to the 1. Because again, when you multiply two exponential terms with the same base, you would add the exponents. Now I have 2 to the k. With this 2 to the k in place, I can now say by the inductive hypothesis that this 2 to the k right here can be replaced with k squared minus 1. And again, it's a total replacement with the greater than or equal to. but I still have a times 2 to the 1, which I'll just write as 2. Now let's see where we can go from there. Somehow I need to show that this is greater than or equal to k squared plus 2k. Let's start by distributing the 2. I get 2k squared minus 2. And so looking at what I want, I'm going to split the 2k squared into a k squared and then another k squared minus 2. So now all I somehow need is for this k squared minus 2 to be greater than or equal to 2k. Well, how in the world do I do that? Technically here, this is not a clear inequality. But, thankfully, let's go back to what we did just a minute ago. Remember, I'm looking at k squared minus 2. Well, look at that. In the last slide, I proved that n squared minus 2 was greater than or equal to 2n, as long as n was at least 3. Now let's go back to my statement. K squared minus 2 I can now say is greater than or equal to 2k, as long as k is greater than or equal to 3. Well, k greater than or equal to 3 is what I did when I started my inductive case. This is why I got a little bit ahead on my base case and did all these first examples, because I knew that I needed k greater than or equal to 3 to do this very step. Now if you had not done some of this in advance, maybe you wouldn't know, oh, I need to get k greater than or equal to 3. But again, the idea is, if you run into a snag and you need k to be a little bit larger, just go back and add a few base cases. We get k squared plus 2k by using the previous slide, since k is greater than or equal to 3. Now we're done. We've shown the inductive step, so we can write our summary sentence. Thus, by induction, 2 to the n is greater than or equal to n squared minus 1 for all n greater than or equal to 0. And that is the end of our proof. Let's do one more example using divisibility. We will start off with our base case. Let n equal 0, and then I need to show that 4 divides 5 to the 0 minus 1. Then 5 to the 0 minus 1 is equal to 1 minus 1, and that's 0. But then I claim that 4 divides 0. Now if you're looking at that and not believing me, you probably have the idea of divides a little bit backwards. Again, this is not saying anything about division by 0. This is saying that 4 is a factor of 0. And sure it is. Anything is a factor of 0 because you can write it as 0 times that factor. Specifically in this case, 0 is equal to 4 times 0. So 4 is a divisor of 0. Now let's do the inductive case. Assume 4 divides 5 to the k plus 1 for some k greater than or equal to 0. Now this time, before I write down what I'm trying to show, let me actually write out what this means. Then 5 to the k plus 1 equals 4l for some l in the integers. Remember, that's the definition of divisibility. So 5 to the k equals 4l minus 1. This statement here will come in handy when we're trying to use our inductive hypothesis. Now let's write down what we're trying to show. Show 4 divides 5 to the k plus 1 plus 1. What I need to do is take 5 to the k plus 1 plus 1 and show somehow that it is a multiple of 4, that I can write it as being equal to 4 times something. With that said, let me go ahead and take 5 to the k plus 1 and start working on it algebraically. Then 5 to the k plus 1 is equal to, and let's use the same technique that I did on the previous slide, 5 to the k times 5 to the 1 plus 1. Now here's where what I told you would help is going to come in handy. The 5 to the k here can be written as 4l minus 1. So let's take this 5 to the k and write it as 4l minus 1, and then I've still got a times 5 plus 1. Again, what I'm shooting for is to try to write this 5 to the k plus 1 as 4 times something. Let's distribute our 5. I get 20l minus 5 plus 1, which is the same thing as 20l minus 4. Hey look, that's a multiple of 4. That's 4 times 5l minus 1, and that's all that I need. Hence, 4 divides 5 to the k plus 1 plus 1. That's the end of our inductive case, so now we just write our summary sentence. Thus, by induction, 4 divides 5 to the n minus 1 for all n greater than or equal to 0, and that is the end of our proof. Let's see what we did in this lesson. How do you prove a statement using induction? What do you think? There's actually 2 steps. The first step is show at least one base case is true by substituting in values. And then step 2 is assume that the statement is true for some k and prove that the statement is true for k plus 1.